Well, hello, everyone. Nice to meet you, if virtually. My name is David Malan. I was class of 1999. To go through the usuals, I was in Matthews Hall, and I was in Mather House thereafter. Found my way to computer science as a concentration after dabbling first with government as a concentration. I came into the university thinking that I was leaning more toward history, government, constitutional, and the law, and the like. But sophomore year, during shopping period, I finally got up the nerve to explore something a little outside of my comfort zone, namely a course called Computer Science 50, an introduction to computer science. And somehow or other, that changed my complete trajectory in life academically. Went on and did my master's and PhD at the School of Engineering and Applied Sciences, formerly the Division of Engineering and Applied Sciences, formerly the Division of Applied Sciences, and ultimately, some years later, found my way back to the helm of that very same class, where I've taught CS50, the same class, for the past 15 years. We were hoping to, of course, gather in person. Weren't sure what to expect in terms of the world goings on, but nice to see everyone here on Zoom, and hope to meet certainly in person before long. Thought I would give you a tour of a bit of history of Harvard, of engineering specifically, give you a sense of what computer science, or CS50 itself is, particularly if you were not in DAS or DEAS or SEAS, and then ultimately give you a sense of how we adapted over the past couple of years, specifically to COVID, but also a look technologically of what we had even been doing up until then. My team and I are involved in quite a bit of online education for Harvard Extension School, for edX, which is the online, massive open online course platform of Harvard and MIT and Berkeley and others. And through executive education, have we been using Zoom and other technologies for quite some time. So I'll give you a sense of the evolution thereof, too. So depending on what class you were, you might remember or have taken a class called ES100, Engineering Sciences 100, which was the first in a path of evolution of classes that were focused particularly for majors or for concentrators on the engineering sciences. Over time, that evolved into a different class known as AM 110, Applied Mathematics 110, which some of you might have taken instead. And then years later, did it evolve further into what was ultimately called Computer Science 150, when there finally was computer science properly at Harvard. In the meantime, there was this other sort of path, another sort of track of courses, if you will, introducing students to engineering, ultimately computer science as well. And many of you might remember Natural Sciences 100 or NatSci 100, which was really the gateway course for so many students into all things technological back in the day. Eventually, that same class evolved into Applied Sciences 10, and then eventually into a course called QR20, Quantitative Reasoning 20. And then somewhere along the way, these two pathways rather started to merge into a set of classes that were both for concentrators and non-concentrators. So yet others of you might recall Applied Sciences 11, which was kind of an amalgam of something from the left with something in the right, that evolved eventually to CS11, and then finally into what we have today and have had since 1989, Computer Science 50, which is the introduction to computer science for concentrators and non-concentrators. It tends now to be among Harvard's largest classes, with some 700 plus students. We convene in Sanders Theater, break off into smaller sections. So quite a few students have found their way, much like myself back in the day, to computer science and engineering by way of this. Just so everyone's on the same page, thought I'd at least give folks a sense of like what it is students today and in yesteryear were learning in a class like this, and really what computer science is. This is computer science in just a few minutes, if you will. But I'd propose that if you're unfamiliar with this field, not an engineer yourself, computer science kind of boils down to this picture here. Computer science is really about problem solving. And even though most of us rather equate it with programming, as do some of our own undergraduates coming into college, of course, from high school, it really is more generally about solving problems. And a problem has input. The goal of that problem solving process is presumably to get output. And somewhere in between there is this proverbial black box wherein the solution to that problem lies. And so the study of computer science is really the study of information and how you get to go from these inputs to these outputs and get answers to questions. But before we can study or even talk about computer science, we all kind of need to agree on how we're going to represent these inputs and outputs. We all need a common language, so to speak. Most of you probably know, if vaguely, that computers speak binary, zeros and ones. But what really does that mean? Well, let's consider how you and I might represent the simplest pieces of information. For instance, how might we count the number of people in this Zoom room? Or in the physical world, how might we take attendance physically? Well, we might do it old school with 1, 2, 3, 4. But of course, how high can I count with just a single hand? It would seem, based on what we learned growing up, that you can count to 5 on one hand, after which you need a second hand if you want to count further. But if we think a little harder about this, it turns out we can draw inspiration from even this sort of old school physical approach. How high could I actually count on one hand if I were a little more clever with how I use my fingers? Anyone want to chime in the chat with how high you can count with a single human hand, even if it looks just like mine? How high can we count, perhaps? It's not just 1, not 2, not 3, not 4, not 5. So Michael proposes in the chat 32. And indeed, we can count 32 things on our fingers, though technically if we start counting at 0, we can count as high as 31. Now, how do we get from 5 fingers to 31 things? Well, at the moment, I'm just kind of putting up my fingers using what's called unary notation, just literally putting them up. And if a digit is up, that means I'm counting someone in the room. But what if I actually took into account the pattern in which my fingers were up? So instead of this being 0, then 1, then 2, then 3, then 4, then 5, what if we're a little more clever and we start to take patterns into account? So we do 0, 1, and then for 2, why don't we do this? For 3, why don't we do this? And we can keep going from there. And so take into account which fingers are up and in which order. That's how we graduate from the unary system to the binary system. Bi implying 2, whereby now we take into account which of our fingers specifically is either down or up. Now, it turns out that this very simple thing, this ability to permute your fingers in a more clever way and therefore count higher, is really kind of how computers do their thing and how they get away with only speaking binaries, zeros and ones, with which we're all probably generally familiar. But why is it that computers rely on just zeros and ones? Well, at the end of the day, this is the only input to any of our laptops, desktops, phones, mainframes, is electricity. At the end of the day, or at some point during the day, you're plugging it in and getting electricity out of the wall. Some electrons are flowing left and right to sort of recharge that particular device. So if the only physical resource that is ever being supplied to these devices is electricity, well, maybe we can kind of harness that and kind of hold on to some of that electricity and use that to remember information. So maybe if there's no electricity present, let's just call that a 0, so to speak. The light bulb is off. But if we hang on to a little bit of electricity that we've stored up, maybe we could say that that computer is now representing a 1. Instead, it's actually now holding a charge. And in fact, inside of our computers, be it a Mac, PC, Android phone, or iPhone, there's thousands, millions of tiny little switches nowadays called transistors. And a transistor is kind of like an old wall switch that can be down and it's off or up and it's on. But it's certainly much smaller than that. And using these tiny little switches can computers hang on to or let go of a little bit of electricity to remember information. And so if you think about these now on a real world scale, inside of a computer really, it's not just these switches, but the equivalent of some light bulbs that can either be on or off. And here, rather faded on screen, is a light bulb that I claim is off. And so computers just by convention assume that if the switch is off, if the light bulb is off, tiny as it is, that is representing the number 0, just like my fist before was representing the same. If, though, they store a little bit of electricity, that 0 can go from an off light bulb to an on light bulb, at which point we would say the computer is storing a 1. So it's like the computer putting the first of those fingers up. But since we're using electricity, and since it's just easier for either electricity to be there or not be there, computers kind of stop counting at 0 and then 1, and that's it. There is no 2, there is no 3, there is no 5, there's no 31. Somehow or other, they ultimately use just zeros and now ones to count even higher than that. And they do this, too, by way of patterns. They don't do it naively like this. For instance, suppose that a fancier computer, we've just upgraded, so our computer no longer has a single switch or a light bulb, but it has 3. And here are those 3 light bulbs, and all of them are off by default. Well, these 3 light bulbs collectively inside of that computer might arguably be representing now the number you and I know as 0. They're just all off. We could count to 1 by turning 1 of them on. We could count to 2 by turning 2 of them on. Or we could count to 3 by turning 3 of them on. But similar to my fingers, that would kind of max out just how high we can count by just having turned those 3 things on, just like my 5 fingers were initially up. What if we start over and actually take into account the order in which these light bulbs are turned on and off, And let me propose that computers instead do this. If you've got an old Mac, an old PC, an old phone, if you will, that has just 3 transistors, 3 light bulbs, if you will, and all 3 are off, we can say that the computer is storing the number 0. If you turn one of them off, specifically this one, now we can say the computer is storing a 1. And if a computer now wants to count to 2, to 3, to 4, we can do this too, as we would need to in a calculator, in Microsoft Excel, in any program that needs to go beyond zeros and ones. This is how a computer would store the number 2. This is how a computer would store the number 3. This is how a computer would store the number 4, 5, 6, 7. And if you're not an engineer, the pattern that just appeared on the screen isn't necessarily obvious, but here's where we can now map it to, again, very familiar ideas as far back as grade school. So here, for instance, is the number you and I obviously all know as 123. We just kind of instinctively know. We see this symbol with like sort of a straight line and then a squiggly line and then a doubly squiggly line. Obviously, that's the number 123. But let's consider how you and I just innately know this nowadays. Well, if you're like me, you grew up learning that the 3 is in the ones place, the ones column. The 2 is in the tens place. The 1 is in the 100s place. And so how do we get from this pattern of numbers, 1, 2, 3, to the mathematical notion of 123? Well, you and I are instantly doing some quick math. 100 times 1 plus 10 times 2 plus 1 times 3 is, of course, 100. Plus 20 plus 3, and there's the number you and I just now innately know as 123. So computers use this same grade school system, but instead of using 1 and 10 and 100 and so forth for those placeholders, they don't use powers of 10, if you will. They're going to use powers of 2. So if we generically present this same pattern, something, 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 with the ones place, tens place, and hundreds place, that, of course, is just 10 to the 0, 10 to the 1, 10 to the 2, and so forth. But a computer, insofar as it only has at its disposal, I claim, zeros and ones, because the power is either off or on. We don't have the luxury inside of these computers of having all 10 digits, 0 through 9, that you and I use as humans. Let's just change the system being used from powers of 10 to powers of 2. So now I claim within each of our Macs, PCs, and phones, what's really going on mathematically is a ones place, a twos place, and a fours place. And so if inside of a computer are 3 light bulbs, all of which are off, aka 0, 0, 0, I'll now say, that is the number, of course, 0, that you and I in the decimal world, dec meaning 10, all know innately as 0. Why? 4 times 0 plus 2 times 0 plus 1 times 0 gives us, of course, 0. How does a computer store the number 1? Using 3 switches or 3 light bulbs, or, if I may now, 3 bits? Binary digits gives us the term bits. This is how a computer would represent the number 1. This is how a computer would represent the number 2, and then 3, and then 4, and then 5, and then 6, and then 7. And so now, using zeros and ones only, and getting rid of the light bulb metaphor altogether, do we have a mechanism where a computer, just using tiny bits of electricity, can count higher than 0, higher than 1, on up to 2, 3, 4, 5, 6, and 7? And let me ask the group via the chat, perhaps, how would a computer go higher than this? What would need to happen for any computer to now count as high as 8 or 9 or 31 or beyond? How do we get higher than 7 inside of any computer, would you say? I'll wait the socially appropriate amount of time in the Zoom chat here. Amanda, might need to cold call on you, if I may. Any thoughts here? More bits, proposes Amanda. Exactly right. So we just need more bits. We need no more light bulbs. We need more transistors. And thankfully, thanks to Moore's law, with which some of you might be generally familiar, computers are getting faster. They're getting more resourceful. They're getting more powerful year after year, which in some sense means we're just getting access to more and more of these switches, more and more of these bits. And so computers can crunch bigger and bigger numbers nowadays and do many other things much faster. But even now, in 2022, what's going on inside our Macs, PCs, phones, and the like is literally just this mechanism, this binary system being implemented in hardware using tiny little bits of electricity to store ultimately numbers like these. Now, if we want to count up to 8 or to 9 or to 10, we of course need more bits, but there's really no end theoretically to how high we can now count and how big these numbers can be. How, though, do we get from just storing numbers inside of a computer's memory to actually doing useful work besides calculating and besides using Excel? How do we actually write text documents using Microsoft Word or Google Documents? How do we actually play games or use any other software on our computers? Well, we're going to minimally need a way of representing not just numbers, but maybe letters of the English alphabet or really any human alphabet. But at the end of the day, and here's where it's perhaps reassuring that as sophisticated as computers now are, they're pretty simple underneath the hood. All you have at your disposal are zeros and ones. So any problem you and I solve with computers nowadays has to be reducible to zeros and ones. So how do we represent English language, A's through Z's? Well, you and I just need to decide cordially in a room what pattern of zeros and ones we're going to use to represent A and B and C and D. And maybe we could keep it simple, like A is 0 and B is 1 and Z is 25. And that is what humans did. It's not quite as simple as that. Years ago, humans decided that the number 65 inside of a computer is used to represent a capital A. 66 is used to represent capital B. 67 for capital C and so forth. But ultimately, it's just that mapping here. So maybe those of you who are engineers or took a class like CS50 or just want to go out on a limb, what message is being stored on the screen here? Assuming that this computer has not just one, not three, but 24 bits. If we count up all of these zeros and ones, there's 24 of them total. And I've deliberately clustered them 8 at a time. So this is, as a hint, a 3-letter word being stored in the way that most any computer would store this 3-letter word. So you can perhaps rack your brain now for just 3-letter words, but even that's a bit of a trick question. If I give you a hint further to say that this is how a computer stores the number 72, is that maybe a hint? If A is 65, B is 66, 67, 68, 69, 70, 71, 72, 72 would be H. So this is an H. This is going to be, if we do the math, this is a 73. And to be clear, how am I getting 73? 1's place, 2's place, 4's place, 8's place, 16's place, and so forth. So I'm just doing some quick mental math. It's not cat, although cat is generally the answer to most questions on the internet, to be fair. This indeed is the word hi with an exclamation point at the end. So truly, if you were to send or receive a text message now or right after this session that someone just wrote in all caps HI exclamation point, what has really happened is your phone or your computer has received a pattern of zeros and ones electrically somehow that represents the number 72, 73, 33, and your Mac or PC or your phone then displays that pattern of zeros and ones as the English text you and I now know. And ultimately, everything is reduced to these zeros and ones, and it really just depends on context how computers interpret them. If you're using Excel, you might literally see the numbers 72, 73, 33. If you're using a calculator, you're definitely going to see the same. But if you're using a text messaging program, you're using Microsoft Word or Google Docs, your computer will present that same pattern to you instead as just representing English or whatever human language you happen to speak. Here's one last one, and no one's going to get this, surely, but you and I have probably sent, received, seen this particular symbol over the past couple of years all too frequently. This pattern of zeros and ones, if we do the math, where this is the ones place, twos place, 4s, 8, 16, 32, 64. This is bigger math, but if we do out the math, this pattern of zeros and ones translates to the number 128,514, which, fun fact, is how a computer would represent electrically this particular emoji, with which you and I are perhaps all too familiar. It's a picture, of course, but it's really just a character in an alphabet. You can think of emoji as indeed just a graphical alphabet, and humans in a room some years ago decided that this particular image shall be represented with this particular number, aka this particular pattern of zeros and ones. And we can go on and on and on and come up with very similar ways to represent colors and images and videos and sounds. But at the end of the day, it's just a global agreement as to how we're storing these patterns of zeros and ones. So that gives us then the mechanism for representing these inputs and outputs. Let's just take a quick glimpse inside of the black box and consider what it is we're spending all of our time in classes like CS50 and all of its predecessors. Well, inside of that black box are these so-called algorithms. Algorithms are just step-by-step instructions for solving some problem. Ultimately, in a class like CS50, students translate algorithms to actual code in programming languages called C and Python and JavaScript and other languages as well. But at the end of the day, algorithms are independent of programming. And indeed, you can be a computer scientist, certainly without ever writing code, but you can still express yourself logically in these step-by-step approaches to solving some problem. And here's a problem that is increasingly unfamiliar to our undergrads. You can even see the symbol on this here phone book. But at the beginning of CS50, do we introduce students to the idea of algorithms by way of this old school device, whereby if you want to search for someone in a phone book, you of course start maybe at the beginning where all of the A names are, then the B names, then the C names. Everything in here, of course, is alphabetized, and you've got all the names and numbers. An explanation I do now have to give at the start of CS50, because students are now just using, of course, devices a little more like this. But it's the same thing. If you're an Android user or an iPhone user and you go to your contacts or you use the phone app and you search for someone, it's actually the same idea, really, even digitally here, right? You've got all of your friends or colleagues' names from A to Z, typically, alphabetized by first name or last name. You might be in the habit of using autocomplete, so you type the first few letters of someone's first or last name, and your phone, wonderfully, is immediately finding that name. But how is it finding it? Well, it turns out it's likely finding it just like you and I were some years, some decades ago when using this equivalent technology. We might start naively, but correctly, from the beginning of the phone book and just look for someone's name. If I'm looking, for instance, for Manda in the phone book, I might start at the first and see, nope, I'm in the A section. So I keep going to the B section and so forth. One page at a time. Now, this algorithm, of course, this step-by-step approach is going to be very slow, especially if I'm looking for Manda or someone whose name maybe even starts with Z. But it is correct, this algorithm. If Manda or whoever I'm looking for is in there, I will find them. But of course, I could do this a little more intelligently, especially if I want to save time. I could maybe do 2 pages at a time. 1, 2, 4, 6, 8, 10, 12, 14, 16, and so forth. That algorithm is going to be twice as fast. But it's not necessarily going to be as correct, because what could go wrong? If I'm flying through the phone book 2 pages at a time, I'll get there much faster, but I could get unlucky, and the person I'm looking for is maybe just sandwiched in between 2 of those pages, so I blow past them, and now I've incorrectly determined that they're not in the phone book. But I can fix that. This would be what we would call in programming a bug, a mistake in your algorithm or logic. But you know what? If I maybe go a little too far, and I go all the way to the, I go just past whatever section of the phone book I'm looking for, well, I can just double back 1 page and recover from that. But of course, you and I, if you remember using this technology, generally don't start at the beginning and naively go from left to right, whether it's 1 or 2 pages at a time. We probably go roughly to the middle, wherever we happen to end up, and then we make a decision. Here, for instance, I've gone too far, and I'm already in the S section of the phone book. But what do I know if I'm looking for Amanda by first name? Well, I know that she's in the left half of the phone book, if this thing is indeed alphabetized. And so as we dramatically do in Sanders, we can then tear this kind of problem in half and now throw away some half of the problem, leaving me really with the same problem fundamentally, but now it's smaller. And I've taken a really big bite out of it. If this is a big phone book, like 1,000 pages, I just threw maybe 500 or so of them away. So same problem still, but way bigger bite than 1 page or 2 pages at a time. And I can continue this, hopefully not destructively doing this again and again. Otherwise, we can only do this algorithm once, but I can ultimately whittle the problem down so much faster. And indeed, if I now assume, for the sake of discussion, a phone book that's got 1,000 pages, the first algorithm might take me like 1,000 naive, slow steps to find someone, especially if they're all the way at the end in the Z section. All right, the second algorithm, a little smarter. It's going to take me like 500 steps maybe to get all the way to the end by naively, but still reasonably going from left to right and doubling back 1 page just in case someone gets sandwiched between. But the third algorithm, if folks are comfy chiming in the chat, if you start with roughly 1,000-page phone book, how many steps will it take you to find anyone maximally that you're looking for. It's not going to be 1,000 steps. It's not going to be 500 steps, even if they're at the end of the phone book or in the middle or in the beginning. Anyone want to ballpark in the chat just how many times really you can tear a 1,000-page phone book in half? It really boils down to a question of 1,000 divided by 2, so to 500, 250, 125, 67-ish. We got to start rounding a little bit there. But 10 times, notes Michael in the chat, 10 times. So indeed, 1,000 pages can be divided in two again and again, divided and conquered, if you will, again and again, just 10 times, which means we've gone from 1,000 steps naively to 500 steps more powerfully, but still pretty slow, to just 10 steps. And so here then again, we have these algorithms. And what we spend time on in every week thereafter in CS50 and computer science courses more generally, independent of programming and specific languages and all of that, is really this idea, focusing on the study of information and really the solving of problems, where we just need to agree how to represent that information and ultimately how to step through it to find some solution to a problem. So years ago, there really was no computer science, at least by this name. Started out as applied mathematics early on, at least when it was a formal study. And way back then, there was no school of engineering. There was no division of engineering. There was no division of applied sciences. There was the Lawrence School, pictured here many years ago, that was where engineering got started at Harvard's many years ago now. This, of course, evolved into a building some of you might recall as Pierce Hall up on Oxford Street, which was home to the School of Engineering ultimately for quite some time. But more recently, did that get supplemented, not pictured yet in this photo here, by Aiken Laboratory, which was home to computer science and other faculty and students as well for some time. It was demolished some years ago in the mid-1990s to make room for a new building, thanks to Steve Ballmer and Bill Gates, named after their mother's maiden names. This is the building known as Maxwell Dworkin. I happen to be class of 1999, so I graduated in the spring of 1999 as a computer science concentrator. This wonderful new building then opened in the fall of 1999 for all of my successors, so never quite spent time there until I returned for graduate school ultimately, but this still is down the road on Oxford Street. But some of you might know now, too, that the School of Engineering is in the process of relocating many of its areas and many of its faculty and now students across the river to Alston, which over the next decades will surely take shape all the more. This is a photograph in the height of the grassy season of the back of the building. This is now known as the Science and Engineering Complex, or SEC. This is across the way on Western Avenue. It's roughly catty-corner from Harvard Business School, or the iLab, if you recall the campus there. So if you walk down the street from Harvard Square, down JFK Street, down North Harvard Street, past the stadium, and hook a left, you'll arrive at this amazing new facility here where computer science and a number of other fields have arrived as well. Was postponed a little bit during COVID, but now faculty, students, and staff are spending time there. Here's a rendition of the entrance into which folks initially walk. It's multiple stories, a lot of big open space, similar in spirit to the iLab at HBS if you've been, but on a much grander scale. And so do, if you get a chance in Cambridge or Alston, visit there before long if you can. And now we'll look at CS50 specifically and how we've adapted over these past couple of years, because this building, for instance, was essentially empty for the past 2 years, even as it was starting to come online. And of course, last year especially, were most everyone off campus. But the number of students that we've been supporting, not only within the School of Engineering, but computer science specifically, has been growing rather astronomically. So this is a diagram, if curious, from 2007 all the way on the left, now most recently to 2022 all the way on the right, and the blue swath in the middle. So this blue part of the image here shows us how many concentrators we had back in 2007, which was roughly 69 undergraduate concentrators. And if we now fast forward to 2022, past the COVID dip, when a lot of students took time off, we're now up to some 504 concentrators in the same field. Above that is applied mathematics in pink, and then down below that are the various subfields of engineering as well. So STEM, science, technology, engineering, and math, math has been markedly growing, certainly on campus as well as elsewhere too. This, though, is CS50 in Sanders Theater, if you recall, having taken any number of classes there or performances. This is in healthier times. This is not in recent memory now, but hopefully this coming fall and beyond will look a little more something like that. To give you a sense of the scale of this particular class nowadays, CS50, we've had most recently about 700 students here on campus or online at Harvard College. The course's own staff nowadays is itself larger than the average class size. We have some 40 teaching fellows who lead sections, grade work, hold office hours and the like. We have some 40 course assistants or CAs who hold office hours and more. In the case of CS50 and computer science in general at Harvard, there's long been a tradition of undergraduates holding these roles. So while we certainly have graduate students filling some of these roles, supermajority of CS50 staff and follow-on classes now are still held by undergraduates, which is a nice long-standing tradition. CS50 for the past 15 years has also been offered via Harvard's Extension School or continuing education program, where most recently we have about 200 students around the world too. Funny enough, CS50 is now offered at Yale University down the road in New Haven, where we've been collaborating for the past 6 years with colleagues there. We film and we hold the lectures here in person in Cambridge, but the students at Yale are able to then watch live or on demand thereafter. But Yale has its own team of teaching assistants to lead sections and office hours and the like. A faculty counterpart of mine officially heads the class there with the course manager who helps run the logistics. And so CS50 happens to be one of the largest classes at Yale nowadays, with most recently some 300 students in New Haven. And in healthy times, we actually have had a tradition of bringing the Yale students up here, or the staff and I visiting New Haven down there to bring the two campuses together. But certainly we do even more of that virtually nowadays as well. They too have about 40 TAs leading those classes as well. And fun fact, even though Harvard in computer science has had undergraduate teaching fellows since the days of Professor Bill Bossert, if you recall the name, in the 1970s, Yale only as of 6 years ago began having undergraduates or undergraduate learning assistants lead sections and grade work and the like. So that now is a new tradition that's been sparked as a result of this collaboration as well. The course is also freely available nowadays as open courseware, so to speak, in the spirit of MIT. We have some 1 million students or casual learners online via YouTube, and over the past several years, since 2012, have more than 3.4 million students registered for free online via edX, which is this, again, massive open online course platform started by Harvard and MIT and Berkeley a few years ago. Which is only to say that not only is this course very much operating at scale here on campus and down the road in New Haven, but also online as well. And indeed, for the past 15 years, has making educational content, this course's educational content, freely available, really evolved into a mission for myself and for my colleagues here in Cambridge, focusing on making available the resources we long have to undergraduates on campus, to really anyone off campus who might like to uplift themselves either professionally, educationally, or just take a passive interest in learning something new. They, of course, don't get nearly the same support structure as you might here on campus in the form of those sections and office hours and the like, but particularly within the sciences and the computer sciences, is it all too technologically feasible for us nowadays to do as much as we can to at least support folks through automated assessment and through automation and digital support structure, even bringing students around the world into our classes now via Zoom, as we are on right now. So traditionally, the course is structured both pre and during COVID around lectures that I lead in Sanders Theater once a week for a couple of hours, wherein we introduce the week's concepts and high-level ideas. Sections or recitations led by the course's undergraduate teaching fellows for smaller groups of students, maybe 6 to 20 or so students total, walking in at a slower pace in more detail into some of the week's material. CS50 offers what we call tutorials, which might be a ratio of 1 to 6 students maximally, opportunities to work on the week's problem set or programming assignment that characterizes most of students' time in this course, writing software and learning how to convert those algorithms into code in some language. And then, of course, office hours, one-on-one or small group opportunities for Q&A about the very same. So when COVID was upon us in March 2020, we were actually in the process of offering a smaller version of CS50 with about, at the time, 60 or so students, in addition to the 700 student version that typically happens in the fall semester. And of course, all of these students then had to head home, and we transitioned ultimately online. Fortunately, at that point, at least technologically or educationally, CS50's team and I had actually been, as mentioned, focusing a lot on executive education via Zoom, focusing on some of our students across the river at HBS to whom we had long live streamed content, which is to say that we've been dabbling in a lot of these technologies, fortunately, before COVID came around. And the setups, the technology we were using, ranged from the simplest. This was me about to lead a class in a conference room with a whole bunch of reams of paper with my laptop stacked above them. And then there's like an HDMI cable here that was leading to like a TV that we found on the wall, just so that I could try to, in this case, lead a particular online class that day. When COVID hit, though, in March 2020, by April or May or so had we begun to experiment really with alternative, more sophisticated solutions that would allow us to better support in real time many more students online with this artist's rendition of my kitchen at home. So pictured here is what was my kitchen counter. Not pictured here is the mess everywhere else. But what you'll see here is the first setup that I, at least myself, was using early on in COVID to teach. We had a tall white backdrop that we found on Amazon that would just give a clean look. We had these LED lights standing up just to splash sufficient light on the screen so we could keep everything well lit and visible for students. We had the same here. And any of you have been in the habit of fine-tuning how you look on camera. Having a bit of light in front of you tends to help too, so that was there. Here I had one of those retractable up-down laptop stands that I propped on top of the counter so that I could raise the webcam roughly to my eye line. So it would look like I'm not just sitting in my kitchen trying to lead a class for all of my students, but I was actually standing there and doing this in my usual way, trying to bring an energy to the class, especially when students are now siloed in their own homes or rooms, just trying to take some class online. And if we zoom in on this setup, this was my laptop, for instance, had a nicer quality webcam propped up on the top just so that it was a little clearer for students, and it felt as close as we could to an actual class and not really as just some plan C or plan D. We were aspiring in this case to at least try to bring some energy, some quality to the experience for students, so it didn't feel like too much ultimately of a differential. Thanks to my very talented colleagues, though, did we rapidly iterate in those early months in 2020, and we started to focus, too, on the user interface, the software. We, and Harvard more generally, were using Zoom, and it's pretty darn good for video, no matter where you are in the world, but its interface isn't the best in terms of the user experience, so to speak. When you're screen sharing, you, the presenter, are relegated to a tiny little square, which for an hour-long, 2-hour-long class isn't really ideal, lest the class devolve into a PowerPoint presentation, really. So we started experimenting with free software, open source software, so to speak, to create an alternative to what would have been the default experience for students in Zoom. So this here is a screenshot of Zoom showing some very arcane code here at left. And it's actually fake code, doesn't do anything useful in this case. And here was me relegated to the little tile that Zoom creates. And for better or for worse, we thought that for me and for any of my colleagues teaching on Zoom, it would be nice to at least bring a little more energy and life to the videos by at least increasing the size of the instructor. And so we did this. Unfortunately, in retrospect, I hadn't really shaved for quite some time because this was early COVID, but we were able to lay out using special free software, just really any layout that we want. So this is a program called OBS, Open Broadcaster software, which allows you to lay out different templates, whether you're using code or slides or video or animation or yourself or the like. And this was just a very early attempt to just try to make things feel more like a class and less like a typical Zoom. When we were allowed a few weeks later to come back on campus, albeit with lots of PPE and very isolated from one another, we found a small conference room off to the side that looked a little something like this. We had painted the back wall green, which lends itself to doing Hollywood-style trickery of putting slides behind you, just like I'm literally doing right now. We had a large table, but most compellingly, we had my laptop at the end of this table, and then just a really big TV at the other end. The hope being for me to try to bring some realism to the experience, to still see and get to know my students without them being relegated to like a 13-inch laptop screen alone. And so if we zoom in on this, what you'll see is not only the students' tiles for this particular class with the names and the text much bigger so I can actually read and call on their names properly. We experimented too with this little teleprompter up here so that we could put secretly the camera behind the teleprompter. Whichever student was asking or answering a question, I would then see their face overlaid on the glass in front of the camera. And this was for the most marginal but I think important of details so that you're actually seeing and the student is seeing eye contact. I mean, all of us have spent probably 2 years with this happening where you don't really notice, or you're looking over here, and it really breaks the illusion that you're having a conversation, that you're having a class. So it was even these finer touches that we tried to get right or make better for students, especially if they'd be doing this for the entire year with us and with others. And then we began to transition back to Sanders Theater itself. There were no students there back in 2020, but we got the requisite permissions and health protocols in place to keep an adequate number of feet away. We had all of the air and cooling was sufficient for filtration and the like. And this is me and a colleague, Andrew, on the stage of Sanders, looking out on what would be an audience where the light is now shining down. But all of the students in this case were actually on this very large TV monitor. So this was an 84-inch TV in front of me now, so we could start to lead even larger classes. And it would feel for students a little more like home, if you will, and not just me in my kitchen, not just me against a green screen, but me at least in Sanders Theater, so that even though they weren't there, at least we could bring some of Harvard to them. So this was sort of the next evolution of that. Beyond that, too, did we begin to experiment now with what I'm actually using right now. I'm here in our studio on campus where I have 3 very large TV screens. So I'm mostly looking here at the camera, but I can see all of you to the left and to the right as well. What that setup looks like behind the scenes is a little something like this. So we have a big white or green backdrop. If we zoom in a little bit on this setup, you'll see the 3 TV screens here. There's a camera up there in the middle. My laptop is literally the laptop I'm manipulating right now. The camera is roughly centered across the screen, and I'm far enough back that even if I'm looking at the TV, the eye line doesn't quite look as bad as it might on a laptop or a desktop computer at home. I have a little confidence monitor here, so I know if I'm accidentally walking way too far out of frame, and this kind of thing doesn't necessarily happen. And then over here, behind this table here, I can actually see a really tall chat window and a really tall Zoom window of participants, so that when we're holding classes for students, be it 20 or 200 or 1,000 students in a setup like this, we can see much of what's going on. Not quite the same as being in person, but again, lowering that bar further. But perhaps the most meaningful experience to have happened to us, at least educationally, experientially, professionally, was the silver lining, or a silver lining, at least for us. In the fall of 2020, we were allowed, a few of us, to come back onto campus, but given that most of the campus was dormant, there was also this opportunity. And if any of you recall the Loeb Drama Center, home of the American Repertory Theater on Brattle Street, which holds plays and performances throughout the year, they, unfortunately, and their whole talented team were idled by COVID as well, since there were no performances, no plays, no rehearsals. But we got the requisite blessing not only to use the space, but to collaborate with that team of artisans and the prop masters and the lighting experts and the sound experts, and were able to use the American Repertory Theater stage to bring CS50 all the more to life. Still no audience, but in a way that actually allowed us to collaborate with that team of artists and bring visually computer science and those zeros and ones all the more to life, in large part because, one, we were able to create our own sets, our own props. We were able to set up for hours on end as opposed to rushing into Sanders, which is a very beautiful space, but also very highly scheduled, such that we need to get out of there right away. So pretty much all we get in Sanders is what I can carry physically on my laptop or the like. We were able to spend the summer and those months of fall bringing the stage to life and the experience and hopefully the content for students alike. So pictured here is the main stage of the American Repertory Theater. All of the lights above, of course, some footlights across the bottom of the stage. And if we zoom in a bit further, you'll actually see a watercolor painting from a Harvard alum from 1794 who was standing there somewhere in Harvard Square painting what is and was Harvard, Harvard Hall, Massachusetts Hall, and one other building that's no longer there. And this was actually an image we found in Hollis, the library system on campus, which had been digitized some years ago. It was tiny, sort of postcard size, but thanks to, ironically, computer science and artificial intelligence, were we able to enhance this thing to be 30 feet tall. And so we brought to life as our backdrop of this set, if you will, that very same picture. And it was, again, meant to be a little opportunity to try to bring Harvard as best we could to the students themselves, and a little something, too, that was otherwise just sitting tucked away in the Harvard archive for quite some time. If we pivot around, this was me tearing, as it turns out, a phone book on stage. No audience there, but they were there via Zoom, as were a duck and some of our other inanimate objects, as well as my colleagues, all covered in PPE. If we flip around, this is what I, as the instructor, was seeing. I had the stage here, and we had the lectern and the laptop, but then I had 6 TV screens or projector screens with as many as 150, 300 students on the screen at once. 150 over here, 150 over here. Not only did we have then the Harvard students and the Yale students tuning in live, if they so choose, although the beauty of the internet too is that they were also tuning in asynchronously, especially for reasons of time code. One of the sets of screens was also for our open courseware initiative, so that literally anyone on the world up to a limit of 1,000 could also tune in, and I could see and interact with them in the absence of active Q&A on the other screens as well. If we zoom in here, this too is what I would see and students would see back when doing Q&A. With students, we would then full screen one of their faces and their names on one of the bigger TVs and approximate as best we could having a conversation with them. But again, thanks to this talented team, not only were we able to produce things, much like a live show, the sort of Emmys or Oscars cutting among all of the various camera angles in the space, we were able to engage students using simple technologies like polling and put their answers and put their interactions up on the screen and bring them into the class itself, even though I was only physically the one there, playing with light bulbs all the more physically, wonderfully using the actual stage lights to bring binary and zeros and ones to life. Being able to do things like this. The ART has an amazing warehouse of like decades of props and costumes and supplies a few towns over that they allowed us to poke around in and decide, wow, we could use this to bring this topic to life and this another. And I'll stipulate for today's purposes that refrigerator, especially with a chain and a padlock on it, is a wonderful metaphor for atomicity and locking a database, so to speak. But more on that, you'll have to take the class. Thanks to the prop shop, we were able to bring computer's memory to life. So pictured here is a lot of Oscar the Grouches representing garbage values in a computer's memory using a prop that we weren't able necessarily to use ourselves in Sanders or something like that, certainly lacking the carpentry talent myself. And then one of the demos I had long, for 14 years, hoped to bring to life is this. This was literally 7 doors on stage, behind which were some secret numbers. And the goal here was to use metaphorically these doors to represent also a computer's memory when searching for information. The sort of demonstration, the visual, that's doable in Sanders if we had a whole week to set up. But during COVID and with the ART, did we have a whole week, a whole month, a whole semester to set these kinds of things up and bring a visual aspect to the class that has otherwise long been more challenging to do anything beyond digitally. So now that we're returning, hopefully, to campus this coming fall, and Harvard has just recently relaxed its masking requirements here on campus, we hope to resume some of our old traditions. And if you ever find yourself in Cambridge in September, this particular course starts with CS50 Puzzle Day, which is just an afternoon of problem solving, unrelated to programming, but that typically brings in healthy time some hundreds of students together to just focus on solving fun riddles and logic problems of sorts for pizza and prizes and more. We have a tradition in Healthy Times of reserving much of a restaurant nearby so as to make a big class feel small, and we invite some 50 or so students to lunch to chat with me, the teaching fellows, alumni, friends from industry as well, just about CS and life outside of college as well. In December, traditionally, we have a CS50 hackathon, where at 7 p.m. we all convene off-site or somewhere large on campus, and at 7 a.m. we all go home, having spent the intervening 12 hours having 2 dinners and 1 breakfast, but also 12 hours of programming, working on students' capstone projects, their final projects. And then lastly, especially if you're in Cambridge this coming December or beyond, is the CS50 Fair, where we gather in the new Smith Center, where the Holyoke Center once was and physically still is, to celebrate all 700 plus students' final projects and what they've created. And we invite all students and faculty and staff on campus. In Healthy Times, it's typically some 2,000 people who come through the space to just look at and delight in and take pride in what students have created. And expressions like these are not uncommon on students' faces. I'll pass along these slides to Amanda afterward, but this is 3 hours of footage from Healthy Times 2019 when we last held the CS50 Fair. Carter, if you're able to maybe search for CS50 Fair 2019 and paste this YouTube URL into the chat, you're welcome to experience it by proxy. If you're interested in learning more about phone books, zeros and ones, and everything in between, you're welcome to join us for free online at cs50.edx.org. But please feel free to reach out if you have any questions as well. And happy to turn things back over to Amanda and any Q&A with the group. But hope to see everyone here in person or in Florida again before long.